Okay. So, I start the new topic MHD turbulence, but it is on the framework of flow with a vector. Now, magnetic field is a like a vector embedded in velocity in the flow in the flow. So, the two vectors basically u and w, but velocity field I formulate as if it is advecting the magnetic field. Okay. And now we will use magnetic field as a b variable, not w. That is standard notation in literature. Okay. So, the topics will be formalism. I will set the equations, the energy transfer in fluxes, then I will just describe few turbulence models. There are many models, but I will describe what I consider important ones, and then dynamo. Okay. So, we will quickly go through these topics. Each of is like one full course, but we will try to do in 1 hour, and we will see. So, formalism. So, let us first set equation for u. So, we already have set equation for u. We need to only worry about Fu. So, that is general formalism. In fact, I do like the way it has been written, and it is very useful to think in a global way, you know. So, let us rewrite that equation for u. Grad P plus Fu vector u, okay, plus nu grad square u. So, what is Fu? So, I am assume constant density. So, we will assume incompressible, which is good approximation for many places, not so good for some astrophysical applications, but it is quite good for sun, earth, they work quite well. Sun, yeah, sun is nearly incompressible roughly, okay, quite good. I will not say best, but it is quite good. For galaxy also, but I will not discuss it, privately we can discuss. So, there are ways to say that incompressible is reasonably okay. Okay, maybe I will make a remark. So, first, no, I think let us skip this, because this will go into various approximations so on. So, Fu, just think of liquid metal. Okay. So, inside the earth there is a lot of metal and there is a magnetic field. So, and it is like molten metal, so it is like water, you know. So, it is incompressible. So, that is what you should think in your head. So, what is the force density? So, this is a force density, right? All of this is rho equal to, this is force density, force per unit volume. Okay. So, what is force density formula for in a electromagnetic fluid, or it is called magnetofluid, you will find this word, fluid which responds to magnetic field. Water does not respond very well, but salt water will respond weakly, but metals will respond heavily. You need free electrons. Okay. So, Fu is J cross B. Current density is like is a Lorentz force. Okay. Now, if you use SI or if you use CGS, then there are different constant in front. Okay, normalization factors. So, I will use SI, I will use CGS, unlike your other courses, but I will use CGS. Okay. So, plasma, I think a lot of people use CGS. So, you will use C 1 by C, C is the speed of light. Now, under MHD approximation, so there is another Maxwell equation which is d by dt, no, dB by dt is J minus, so 4 pi by Cj minus curl of E, plus or minus, I should know, curl of E, curl of B, and these are d by dt, right, plus, okay. But in MHD approximation we drop this term. So, we assume that electric field is much smaller than B. Now, I will not describe this approximation, justification and so on, with this what is assumed. So, electric field is much smaller, is highly conducting fluid. So, conductivity is tending to infinity, and for that this is a good approximation. So, we will focus on energy transfers, fluxes, models. We will not discuss too much into these details. Okay. So, If you put that in, you will get Cc. So 4 pi by C, no, C by, I made too many mistakes, C by 4 pi. So Cc cancels, so you get J is curl of B by 4 pi. Okay, and the density I am assuming 1 right now, but the density also comes. So in fact, forcefully there is a density should be sitting here. Force density. So you divide by rho. Okay, so this is formula for Fu. So force on U is depends on B. So that means B must be passive scalar or active scalar? Active scalar. So B affects U. So B is a active scalar, an active scalar. No, active vector, sorry, not that. B is an active vector. Okay. So our formula which I derived for passive vector will not work. Okay. So, and moreover, this force is quite nonlinear. Is B. So, it is a nonlinear force, unlike buoyancy force which is linear. Buoyancy was theta, no, or density. So, this is nonlinear force. So, that makes life reasonably complicated for MHD. Okay. So, this is what we have to keep in mind, that our force is curl of B cross B. In fact, we can simplify this force. Let me write it here. So, we can write curl of B cross B as minus curl of B squared by 2, the 1 by 4 pi rho is outside, plus B dot grad B. So, this is an interesting form. Why it is interesting? But this part can be absorbed with pressure, right. So, we can take this part. So, I say minus grad P plus B squared by 8 pi rho, and the other part is B dot grad B by 4 pi rho. Okay, interesting, no? So, this is called total pressure. So, it is a hydro pressure P plus B squared by 4 pi rho, which is 8 pi rho, which is coming from magnetic pressure. So, P is called thermodynamic pressure plus magnetic pressure. Okay. So, this is the total pressure, and this is the, so I am missing out some vector signs, but they are all vectors. So, this is our force which is nonlinear, well this is also nonlinear, but you remember the pressure does not participate in energy transfers. So, this term will be silent on energy transfers, and we make another change of variable. So, I will make a remark here. In CGS, you make this variable B by 4 pi root rho, this has dimension of velocity. Okay. Now, this BCGS, okay, this is dimension of velocity. So, we make a change of variable BCGS to this. So, this is very convenient, no? Now, B has a dimension of velocity. So, we can write this as, this part is B dot grad B, and 4 pi rho has disappeared. Okay. So, now let us go to velocity magnetic field. So, magnetic field equation, we will again borrow the equation for active vector or for the vector. So, instead of W I am just writing as B. So, dB by dt plus U dot grad B. Now, the right hand side is Fw plus eta grad square B. So, I need to derive this from some Maxwell equation. So, which Maxwell equation I should use? So, we have one equation is curl of E is minus dB by dt, and in CGS E and B have same dimension. So, there must be 1 by C here. Okay, now these are nitpicking on dimensions, but I will not. I will basically ignore units, rather I will ignore this constants, but this one there must be C. Now, E in an MHD approximation is minus V. So, in the moving frame of the fluid, If you go with the fluid, the electric field inside is 0 for ideal flow. No, electric field inside a conductor is 0. So E plus, so by Maxwell, not by Maxwell, by the relativistic transformation, electric field inside the fluid is this, under U by C much less than 1. Okay, there is a transformation of E and B under relativity. So, you will find this is my E prime. Okay. So, this will assume to be 0, but if the conductivity is large, then this is J by sigma. Now, if I were to want to get the proper units, no, I do not derive it here. Okay. So, there is a J by sigma, but there is a some appropriate factor. Okay. So, I can find E, no? E is minus V cross B by C plus J by sigma, which is curl of B. In fact, eta comes here, magnetic diffusivity. Okay. So, plug this in. If you plug this in for electric field here, if you plug this in, then I will get a term for FW. So, this you define, this is how we derive equation for B. So, I write down the equation. Okay. Now, so FW under my new units, my units where B is in the terms of velocity, FW is B dot grad U. Okay, so it is simple, it is nothing complicated. So, you have to use the formula curl of A cross B or curl of U cross B, and you will get this. In fact, you can also write another way, dB by dt is curl of U cross B. Now, these derivations I am not emphasizing because of lack of time, but these are interesting derivations. Now, this equation looks very similar to another equation which is seen in the course. So, equation for the vorticity. No? So, B and W are similar, in fact, they are not identical, but the equation is identical, but they are not same because vorticity is curl of U, but B is an independent vector. That is the difference, otherwise equation is exactly the same. And also some of the dynamics. So, vorticity is stretched by the velocity field, and this is called stretching of the vorticity. No? Same thing happens for the magnetic field. Magnetic field is stretched by the velocity field, and that is how the magnetic field increases in dynamo. So, magnetic field is generated by this process of stretching of magnetic field. Okay. So, maybe briefly I will describe it in the end. Okay. So, this is the equation for B. Now, so this is the advection term, and this is U is acting on B, of course. So, this is like B dot grad U, but it has very similar form as U dot grad B, no, except B has come before and U has gone later. So, these are similar nonlinear terms. So, what is the conservation loss? Now, because of Fu and Fb, U squared is not conserved. Fu is not 0, right? I mean, if you put in magnetic field, I cannot set the force to be 0, and Fb is also not 0. So, they make the conservation law quite complicated. So, U squared is not conserved, B squared is also not conserved, but together they are conserved. This is called total energy. So, integral, no? Integral of this quantity over whole space is conserved. Another quantity called Hc is called cross helicity, which is defined as half U dot B. So, U dot B. Right now I am keeping B as a total field. It can have also mean component. So, B field could be B naught plus B, but when I put a B naught, U is fluctuating, so B naught will not contribute, no, because that will get cancelled. U dot B naught will be 0. So, this is same as half U dot B. Okay. And another constant which is constraint, which is constant, is kinetic helicity, magnetic helicity, magnetic helicity, which is half A dot B. A is a vector potential. Okay, so curl of A is B. So proof I will not discuss, but these are three conserved quantities for MHD. U square and B square are not conserved individually, the total is. This for 3D, 2D has certain modification, but we will skip 2D discussion. Okay. Now, in Fourier space, how the equation look like? So, it's again, I mean, it's straightforward if you just have to look at your notes and pick up the threads. So, EQ dt plus NU. So, my notation in the paper in this book is okay. So, I write like NU of k and minus I k vector P of k plus Fu of k is force. So, this function of k and minus nu k square U k. Some things are coming here. Okay, I am going to write Nu and Fu soon. And for B, NB of k, nonlinear term coming from U dot grad B, and there is a F B of k minus eta k square B of k. Now, Nu of k you know already, right? So, let us for completeness I write it here, k dot U of q, U of p, q is k minus p, correct? What about NB of k? All vectors, huh? No minus, this plus I k dot UQ B of p. Fu, it is B dot grad B. B is also divergence free, right? So, you can write them as del J Bj Bi. Yes. So, you know what is del J Ui Uj. So, it is very similar. So, I k dot B of q B of p, right? It is straightforward. And F B of p, F B of k. So, this comes from B dot grad U. Remember, I just derived it in the last slide. So, this will be del J Bj Ui. So, which is the head vector? Bj. Bj is one which comes with thing. So, it is going to I k dot Bq U of p. So, it is straightforward, and these are the terms which will exchange energy among modes. They transfer energy from one to other. Okay, so, you will see that very nice way to interpret these transfers and derive flux formulas. So, I will make one more discussion is Alfvén waves. So, these are the waves. So, in hydrodynamic flows there is no really wave, though some of you have got ODEs which are not like wave solutions, but there are oscillations, right? Like we found that 3-mode model has oscillations, but there is no wave really. But MHD has waves. If you turn off the nonlinear term, we get wave solution. And what is the wave solution? So, let me just make it linear equation. So, B gives you one term. Huh? So, the pressure part is minus E k P of k. So, this P is total pressure, okay? But there is a term comes linear term is B dot grad B. So, B is a total B. So, I can write as B naught dot grad B naught dot grad b, right. So, I can write this as in Fourier space I b naught dot k b of k. So, this is a term coming from b naught, and the equation for b also has a term which is coming from b naught. In the right hand side, remember, you have b naught dot grad u, right. So, these are linear terms because v naught is a constant. So, the term which comes as I b naught dot u of k. Okay. So, these are two linear equations. I turn off viscosity and diffusivity. So, we can solve for them. Now, is there in the notes. You solve, then you get two solutions. So, we apply magnetic field along z direction. Then, if the wave vector is along any direction, wave vector can be along any direction. So, this is the direction k. Then you get a solution where u and b are in opposite direction. Can you see that? U is here and b is there, and they will oscillate. And also the wave will move. Wave moves with c plus alpha in speed, and the c plus is b naught dot k. So, the alpha in speed is b naught dot k cap. So, thanks to Narendra. So, this is because it has dimension of velocity only if it is k cap. Okay. So, this angle is zeta, so b naught cos zeta is the magnitude of the alpha in speed, which is different for different zetas. So, that is why it becomes 0 for zeta equal to 90. Okay. This derivation I am skipping, lack of time. Is nice derivation, we can do it yourself, but so c plus moves with b naught k, and solution is u and b are opposite and they are equal. So, this is the beauty of this unit, that u and b have same dimension and in fact they are equal. So, the equipartition of. So, if you look at kinetic energy and magnetic energy on the average, they are equal. So, there is another solution. If b naught is in that direction, same thing, but k is going rightward, the wave moves in the minus k direction. Okay, wave is moving in c minus in that direction with the same magnitude b naught dot k, but it goes in the opposite direction. So, there is a wave which is going in that direction, the wave going in that direction for a given k. Okay. And for this, u and b are in the same direction. So, if u is here, then b will be same. Okay. So, these are called alpha in waves, and these are fluid mode, these are wave modes in a MHD, and they have very important role to play in the dynamics. Okay. Now, this I am very briefly describing it. Now, we also have variable called z plus and z minus. Any questions?
Small b dot k is also 0.
Small?
Small b dot k is also 0 or not?
Yeah, that is 0 because of incompressibility. So, small b is perpendicular to k, right. So, fluctuations are perpendicular to k always. There is one subtle point. What happens when your wave is along x axis or k is along x axis? What happens to b naught dot k? Is 0, no? Cos 90 is 0. So, there is no wave on the plane, on the equatorial plane. So, theta equal to 90 degree has no alpha in waves. Okay. And so, there nonlinear term plays a big role on the wave on the plane. Now, we have two variables z plus and z minus. We define it for convenience, u plus b and u minus b. Okay. So, given b, you can write always z plus z minus, sum and difference, and the equations are much nicer in z plus and z minus. Okay. So, let me write that equation. In fact, this was for, in fact, we do a lot of work with that. So, let me write the equation for z plus dot vector. So, there is a mean magnetic field. Okay. It is a minus I b naught dot k z plus z minus dot grad z plus is minus grad pressure plus viscous terms, okay, but I am not, well, let me write this. I will not really discuss this stuff. Nu plus a minus r, nu plus minus eta by 2. The equations are nice, no? Because now we do not have 4 nonlinear terms. We have one z minus dot grad z plus. This for z plus. What happens to z minus? You just flip plus to minus. It is symmetric in plus minus, and except this sign becomes plus, because wave moves in opposite direction. Okay. So these are convenient nonlinear terms, which I will discuss in the next set of discussion. So what will be the nonlinear term, by the way, n in Fourier space? N plus. In fact, I write this as nz plus to differentiate between helical plus and helical minus. There are too many pluses if you write f for everything. So there is helical plus and helical minus, no? So I write nz plus, which is going to be I k dot z minus of q and z plus of p. Okay. So this is my equation, sum over p. Okay. So I think this is the last slide. Thank you.